Hi all, I'm Dr. Banish and I will be leading you through this presentation, which is part of your Chemical Engineering 299 class. So before we kind of start off, I want to again welcome you to Chemical and Materials Engineering at UAH. What we're going to talk about is a path through your sophomore and then through your junior and senior years. So when you think of chemical engineering, is hopefully you think about a process, about things moving and engineers making something and making it correctly. Okay? So our chair, who you will meet both this year, next year, and the year after, so in your sophomore year, in your junior year, and in your senior year, is Dr. Subramanian. She will be teaching you Chemical Engineering 244 in the spring. Okay. Other faculty, so besides me, which you'll see me in 201, which hopefully you all are now. I sometimes do teach Chemical Engineering 244, the Materials class 294. I've taught Thermo before, and then the Advanced Materials class 494. Dr. Yu Lei, who's another associate professor in our department, teaches thermodynamics and kinetics and reactor design. Dr. Kung Ho Roh is primarily on the biotech track, but he also teaches the polymer engineering class for the materials concentration. So you'll run into him also. You'll see him when you are a senior. Okay. Other faculty, Dr. Isaac Torres just joined us. He will teach your computational methods. Dr. Weimer teaches the transport classes 342 and 443. Mr. Quigley has a lot of industry experience, and he joined us a couple of years ago. He teaches your unit operations, your transport equipment, and your senior design course. And again, he's got 30 or 40 years of experience in industry, so he brings a wealth of knowledge with him. Dr. Chen Zhang, who graduated from UAH several years ago, teaches 445, the process control class, so how you control a process. We have Mrs. Catherine Soderberg Dowd, who teaches your safety class. She's a specialist, comes out of Marshall Space Flight Center. And then Miss Angela Hewlett, who is the departmental administrative assistant, and she just does all the important stuff. We do the easy stuff. Okay. So I want to go through this path, is this motivation for your studies, and sometimes there's still a little bit of confusion between what's an engineer, what's a scientist, what's an inventor. Okay. We'll talk about the chemical engineering curriculum, what you are in right now, what you can expect, okay, and then a little bit of advice for you. Okay. So what's the difference between a chemist and a chemical engineer? So normally the way that we think about it is a chemist is responsible or is credited with the discovery of a certain process. Okay? And they may figure out a lot of the kinetics and a lot of the process mechanisms, but it gets turned over to a chemical engineer, okay, to enable and to scale up that process so that you can actually produce what are commercial, industrial quantities of that material. Okay? And we'll give an example later as far as penicillin goes. You know, penicillin was a wonderful drug when it came out, but one of the problems was how do you scale up the production so it can come into widespread use? And that's where chemical engineers take over. Okay? So how we think of it is that chemical engineers use their science knowledge to create and control technology for the safe production of chemicals in a global economy. Okay? Scientists add to the knowledge base. Engineers use science to create and control technology. And then inventors we think of as inventing new technology. That is not just specific to inventors. Okay? Chemical engineers are really good at inventing or creating new technology also. Okay. So if we look at scientists, and you've looked at all of these historically, some of these names you'll recognize, some of these names you may not totally recognize, as we have Newton, Einstein, Curie, Fleury, and Ziegler. Okay. So these two are associated with catalysts, things that we use for polymer production. They were engineers, or sorry, they were scientists, they were not engineers. Okay. Inventors, we think of as Bell, Edison, Ford, Steve Jobs, Bill Gates. So those come down in the inventor side, but they have whole corporations that are built around them, okay, so that that technology or that new idea can be implemented, okay. And then engineers you may not be all that familiar with. One, they are kind of discipline specific, okay, and they're developing individual processes. And you'll hear about these inventors later as you go through your classes. So we have McCabe, Crothers, Brenner, Rouleau, and Pinsky. Okay? So like I say, we'll talk about those later, and that'll even be one of your assignments out of this particular course or this section. Okay? So let's talk about your curriculum. And many of you are familiar with this curriculum, is that you've all gone through your first year now. So you've had a couple of math courses. Most of you are finishing up or have finished up your freshman chemistry. You've started into physics. You've started your liberal arts portion of it, is that you've had your English and maybe a couple of other courses. You've had Engineering 101, which is a computer methods course. And now most of you are probably in this second block, in this year 2 block, where again, you're still kind of in the middle of your math. You're doing your organic chemistry, finishing up your physics, and for engineering, you're in Chemical Engineering 201, which is a general introduction to chemical processes. So what we say out of that course, the singular thought out of that course, is that we have mass in equals mass out, is that there is a balance of the mass in the equations for the reactants and then for the products. That will be expanded on, and you'll come to more complicated situations in Chemical Engineering 244. And then simultaneously with Chemical Engineering 244 is you will be taking your first thermodynamics course. And then when you jump into your junior year, then you start to get a very heavy concentration of your engineering courses. Out of the mechanical engineering department, you'll take statics and fluid dynamics. And then from us is that you will take the quantitative methods for chemical engineers, the second half of chemical engineering thermodynamics. You'll take nature and properties of materials. You will take transport phenomenon, take kinetics and reactor design, and then you'll take unit operations, or the first unit operations. And then as a senior, then you'll take a series of more complicated courses that really start to pull all of your knowledge together, okay? That all the knowledge that you've gained from these first 3 years really start together, okay? And so that you see the interrelationship of everything. In your junior and senior years, then you're going to start whatever your concentration track is. For those of you that pick materials, then you're going to take a polymer chemistry class, you're going to take polymer engineering, and then advanced materials. On the biotechnology side, you're going to take general biochemistry, bioprocess engineering, and bioseparations. And so those will kind of fill you out as you go through these. Okay? Each thing, okay, typically has several prerequisites for it. Is that in these classes you are supposed to learn something, okay, a piece of base knowledge that is then necessary for successful completion of each of these courses. Okay? And if you are welcome to get with the faculty, and we can discuss your specific program of study and where you are and what you're supposed to learn in these courses, and we'd be happy to do that with you. Okay? So this curriculum changed couple of years ago. It is now very, very similar to 70 or 80% of the other chemical engineering curriculum throughout this country. So it's very similar. So when you talk to other chemical engineers at other schools, there may be slightly different names to some of these courses, but you're basically learning the same base material. Okay. So what makes the chemical engineer different than any other kind of engineer? Okay? So engineering has a basis in that you need to have a good background in mathematics and you need to have a good background in physics. And this is true no matter what branch of engineering you go through. Okay? Chemical engineering becomes a little bit special, okay, in that you need to have a good knowledge of chemistry. We're not trying to teach you to be chemists, or we're not trying to make you chemists, but you're going to be dealing with chemical processes, and you have to at least be familiar with the chemistry and the chemical terms behind them. And then more importantly, biology is coming into chemical engineering. As we talk about the use of genes, is that we produce a lot of products from biochemical or biotechnical reactions. Okay? So what we're doing is we are preparing you to go into a whole variety of fields. Okay? There are schools, okay, that teach you basically one thing. Okay? If you look at ceramic engineering, you can go on the web and you can look up ceramic engineering, and you will see a list of a half a dozen schools. Okay? And so there's a very specialized program in ceramic engineering. So if you really want to be a ceramic engineer and you want to start out doing that as a freshman, then there is a program for you. Right? We try to prepare you for a wide variety of fields. One of the things to remember is that your college experience lasts about 4 years. Your work life will last about 40 years. So what we're trying to do is give you the basis so that you can work for the next 40 years. Or if you're really successful and really lucky, maybe only the next 20 or 30 years. So we do that, and we are judged, and you are one of the classes that will hear a lot about ABET. Okay? The Accreditation Board of Engineering and Technology, okay, is what it stands for. Okay? And built into that are several student outcomes. Okay? And these are addressed by your coursework. We get graded on them. Okay? We get graded in that we are giving you problems that fill within these certain criteria or these certain outcomes. Okay? And the first one is an ability to identify, formulate, and solve complex engineering problems by applying principles of engineering, science, and mathematics. And so as we go through each course, okay, and we take a question, an exam question or a homework question, and then we say, can we show the accreditors that the students know this? Okay? Do they know how to identify, formulate, and solve a problem? Okay? An ability, second one is an ability to apply engineering design to produce solutions that meet specified needs, okay, with consideration of public health, safety, and welfare, as well as global cultural, society, environmental, and economic factors. Okay? So this one we kind of do a little bit later in your coursework. There's a couple of questions that we can kind of build up. This is obviously a more complex question, but it's something that the evaluators, and the evaluators come from industry, and so it's important for you to be successful that we start to instill these solutions into you. Okay? Others, can you communicate effectively with a wide range of audiences? Okay? You are not going to just be talking to other chemical engineers. You may talk with members of the public that we call, that have very little science background, okay? and you have to learn to communicate with them, to put your ideas forward, to put your solutions forward to them. Okay? You may be dealing with other types of engineers, and you have to be able to communicate. Okay? Critically important is the next one. Okay? An ability to recognize ethical and professional responsibility in engineering situations and make informed judgments which must consider the impact of engineering solutions in global economic, environmental, and societal text. Okay? So there's an overarching theme here, okay, is that you have to put it in the context of global, environmental, and societal text. Okay? Also, you don't want to be the engineer, okay, that let some bad accident happen. Okay? Because you were not exercising your professional responsibility. Okay? An ability to function effectively on a team whose members either together provide leadership, create a collaborative and inclusive environment, establish goals, plan tasks, and meet objectives. So the last one is really meet the objective. Okay? We do this by teams. No, for most of the problems that we look at, okay, no single person can work through all of the solution. You have to work on a team. That team needs to be inclusive. It has to have divergent points of view. You don't want everybody from the same university with exactly the same training working on a particular problem. You want people that have a little bit different thought processes working with you to come up with a solution that works globally. Okay? And in globally, I don't mean across the world. I mean globally in terms of an industry. Okay? We expect you, and these things are kind of easy. Okay? This is more so what you're working on now, is analyze and interpret data and use engineering judgment to draw conclusions. So that's a lot of what you're doing in your sophomore and then in your junior years. Okay? And importantly, okay, is an ability to acquire and apply new knowledge as needed using appropriate learning strategies. Okay? Is 30 or 40 years ago, when your parents were in school, is that biology was not a big part of chemical engineering. It was just maybe starting to have some influence on chemical engineering. Now biology is a big part of that. So that ability that you can go back as new ideas come in and you can apply that knowledge becomes very, very important. So that's one of the things that we will stress with you, and that is one of the ABET outcomes. Okay? And we'll talk about a specific example later in terms of ABET outcomes, a process that you will learn about. Okay? So your foundation for all of this, okay, is you have 15 hours of math, you have 32 hours of science. Okay? This covers applying the principles of engineering, science, and mathematics. Okay? And then you have your arts, humanities, and social science. So at a school like UAH, you take 27 hours of these courses. Okay? This comes into communicate effectively, learning about ethical and professional responsibilities, and acquire and apply new knowledge, okay? And then function effectively on a team, okay? All of these are critical items in your success, okay? I was at an engineering conference not too many years ago, and I had a lady from Exxon, a vice president from Exxon, was the keynote speaker, okay? And her statement to us as educators, okay, is I need you to teach them to communicate, and I need you to teach them to work on diverse teams. She said, they come out with really, really good technical knowledge, but they don't know how to talk to each other, they don't know how to work on a team, they don't know how to talk to management. So that's one of the things that we try to stress with you, and one of the things that you need to realize is that it's just not your technical knowledge that will be important for you to really succeed, is you have to be able to do these other things. All right? So the way that we kind of break down our curriculum in terms of things that we're going to teach you, okay, is that we have processes and thermodynamics. We have processes, reaction modeling and prediction. We have transport of mass and heat. We have laboratory practice, okay? Can you go into a laboratory and work? Do you understand what chemical engineering is about? And then fluids transport. And then these have several classes that are included in each of those groups. So in the concept of process and thermodynamics, we have chemical engineering 201, 244, and then 344. In the process reaction modeling and prediction is we have the computational class 347, and then chemical engineering 441, kinetics and reactor design, okay? And then finally the process control class. If we look at transport of mass and heat, those two primary courses are chemical engineering 342 and chemical engineering 443. Okay? Laboratory practice are the nature and properties of materials lab, and then the two unit operation courses, unit operation laboratory courses. And then in fluids is we have the mechanical engineering 310, fluids transport, and then chemical engineering 443 and 446. Okay? And this kind of all gets capped off in a couple of senior courses. Okay? And these are the last semester of your senior year. Okay? So we have senior design, okay? And then we have process safety and toxicology. And then you have your two concentration areas, chemical engineering, biotechnology, chemical engineering 460 and 461, and then the materials engineering, which is 494 and 495. Okay. So these, again, you'll decide about in the beginning of your junior year. Okay. You can start thinking about them now, but you don't need to make the choice. Okay. So hopefully everything comes together for you at the end, and you have strength in all of these areas. Okay, so we have all of these areas, and what are we really trying to do with you? Okay, and again, that has the concept of that you can take your base knowledge, you can take your engineering knowledge, okay, and you can start to apply it to new technologies, to new problems. Okay. So polymers we pick as one of the examples. So nylon was invented in 1935, okay, by Carruthers. That was one of the engineers that we talked about at DuPont. Okay, DuPont became very successful in making nylon. Okay, after that, about 30 years after that, then came Nomex. Which is a fire retardant material. So you have the fireman here dressed up in a Nomex suit. Okay? Again, very, very useful polymer. Okay? Kevlar came in 1965. So Kevlar is a very, very structurally strong material. You think of it in terms of bulletproof things, okay, or projectile resilient things. Is that it also has strength for aircraft wings, for covering of wings and other devices. Okay, Gore-Tex, okay, by Robert Gore in 1969. We all love those Gore-Tex jackets. Okay, that's not a new polymer. Okay, but it was a new way of processing. Okay, where he took Teflon and processed it in a certain way, okay, and got this wonderful fabric known as Gore-Tex. Okay? And then carbon fiber. We use carbon fiber for a lot nowadays. Okay? One of the examples would be wings or wing struts. Okay? Carbon fiber has been around since the 1860s. In fact, if we go back to Edison used carbon fiber as his first light bulb filaments. But it wasn't until much later in this century that we started to understand how to use carbon fiber as a true structural material. Okay? Now it's starting to move through the industry like that. Okay? For those of you in bioprocess engineering, the example that we can pull out is penicillin. Okay? So penicillin is produced by a certain bacteria. Okay? It was discovered that it helps to kill other harmful bacteria. That was in 1928. Okay. 15 years later, or almost 15 years later, okay, we were to the point where we could produce 1,000th of a gram per liter of penicillin. So penicillin, while it was a wonderful material, still had production problems. Okay? If you think of 1,000 liters of fluid, you can produce a gram of penicillin. That doesn't let you help an awful lot of people. So there was a real problem with the engineering scale-up. Okay? So nowadays, or about a decade ago, we can produce 50 grams a liter. Okay? So we have increased our production capability by a factor of almost 100,000, okay, in those 50 or 60 years. Okay? And this becomes very important. It's a nice, clean process. Okay? So it's a continuous innovation in bioprocess engineering. Okay? So things that you probably already know about but don't really maybe think about is that we had the discovery of the structure of DNA in the 1950s. And then later is that we had in the 1990s to 2000 is we had the Human Genome Project. And again, this becomes an example of how we apply engineering. When this project first started, we thought it would take 40 or 50 years to do this. Okay? There was some innovation in the technology, a lot of innovation in the technology, and we finished this in less than a decade, or in slightly longer than a decade. Okay? And nowadays, we are talking about gene editing and gene therapy. So we're coming to the concept of individualized medicine, okay? And that is through a process of science, engineering, and then further engineering. So when you think of your education, what am I learning in biology? What am I learning in chemistry? Take some of these examples, okay, and say, here's this basic fact. If I have one more piece of knowledge, can I then use it to start to have beneficial effects for society? So looking at other vaccines or looking through other technologies, okay, just in the last decade, is that we had the H1N1 influenza virus that came on, that hit the population in 2009, okay, is that all of a sudden we ramped up vaccine production, and then we had 4 vaccines, okay, and this was an influenza that then was tamped down very effectively, very rapidly by the introduction of these vaccines. Okay? So in 2009 is that we had a vaccine for the prevention of cervical cancer. Okay? Is in 2012 we had the first seasonal flu vaccine that was manufactured using cell culture technology. In 2014, we had Gardasil 9, which is the first HPV vaccine in the United States. Okay? And then in 2019 is that we had the first vaccine for the prevention of the Ebola virus disease. So things happen very rapidly, and they happen particularly rapidly now that we've got the technology behind us, so we can really apply that technology to help the human condition. Right? And you should not forget to make your employer money, and that's how you stay employed. Right? So going back and talking about the different ABET criteria and chemical processes. So the one that we can look at, or an example that we'll take, is the ammonia synthesis process. This was discovered by Haber and then Bosch, which is why we call it the Haber-Bosch process. Haber was a physical chemist, Bosch was an engineer. Okay? The process for making ammonia for fertilizer is nitrogen plus hydrogen, then goes to ammonia. When it was discovered to do this process is you used osmium, which is a precious metal, as the catalyst. Okay? So what Bosch came in and did was that he discovered that if you did the process at high temperature, is that you could use plain old iron as the catalyst. So all of a sudden the production of ammonia skyrocketed. Okay? So this was really the start of the chemical industry. This process is responsible for 95% of the nitrogen in the human body. Okay? The process is used to make fertilizer. For this, we can make better crops, or we can grow crops more robustly, more of them, so we can fight hunger. It's also used for rocket fuels to explore space. Okay? So this kind of covers ABET Outcome 2, an ability to apply engineering design to produce solutions that meet specified needs with considerations of public health, safety, and their welfare, as well as global, cultural, societal, environmental, and economic factors. Okay? The process is also used for making of explosives. Okay? And this then comes into Outcome 4, is an ability to recognize ethical and professional responsibilities in engineering solutions and make informed judgments, which must consider the impact of engineering solutions in global, economic, environmental, and societal contexts. So in this case, okay, this kills some people, okay, or kills more people. It's also useful. We use it a lot in mining, okay, but this ability to fight hunger and to do exploration, okay, is hopefully a bigger part of this. So you see that almost everything we do can have potentially a very positive and then some negative consequences. Okay? So other famous chemical engineers, okay, are Rouleau. So he was responsible for the multiple effect evaporator. You'll learn about this later. McCabe-Thiele, okay, this is a graphical way to analyze the behavior of distillation columns. This was an important first step in doing this. Now we use a lot of computer simulations, but they still come back to this basic methodology. Okay? Thence, the equation for calculating the minimum number of theoretical plates needed for distillation towers with total reflux. You want to make gasoline? What you use is you use a distillation tower, and you have a certain number of theoretical plates in that, so very important. Carruthers, so we've talked about this a couple times. He invented nylon at DuPont. Okay? Ziegler was responsible for titanium-based catalysts, along with Nada. So we can make these stereo regular polymers. Polypropylene is the main one, okay? And this has opened up the commercial manufacturing of various polymers since 1956. For you guys, it is hard to think that a wide range of plastics didn't exist until the middle 1950s or the 1960s. Okay? And following, last but not least, is Brenner, who worked at fluids flow at low Reynolds numbers. This may seem like a really boring statement to you, but this is very important in nanotechnology, okay, where you are really sinking things down to a small scale, and the fluid flow is very, very low. So talking about things for you to succeed. Okay, so we've had a few examples of some very short case studies and some inventors and the idea behind scientists, engineers, and inventors. But how do you help yourself through this? We have a plan for you, okay? And at this point it becomes up to you to implement the plan for yourself, okay? And one of those things is that you have to be the master of your own learning. Is that you need to be committed to all of your coursework. You don't know when you're going to pull that one piece of information back that is going to be very, very important to you or to your employer. Okay? Make quality study time. So you've heard this through many years. In engineering, it becomes important. It's not just study alone, okay? You need to study alone to get the basics cemented in your brain, and then working with other people, working with teams, working with groups, so that you can really flush out what you know and what you don't know about that material, okay? Obviously, stay up with your coursework, okay? Don't fall behind, okay? Learn the material that is presented in your class. So, chemical engineering is a very traditional engineering discipline. Things are laid out, and each piece of material, as I've tried to convince you, okay, is important not only for that class, but for later classes. If you happen to miss material, then find out about what you missed. Just don't assume that it isn't important, okay? Understand rather than memorize. So this is a critical step, is that you understand the equation rather than memorize the equation and one particular solutions. Okay? If you don't understand what is going on, then get answers to your questions. So the faculty in this department at UAH are very happy to help you. We are committed to you having the best experience as you come out of this program, and we want you to succeed in life. Okay? And then tied into this understand rather than memorize is to learn the broad concepts. Right? Is look across engineering as a global thing, okay, composed of many, many parts. Okay. So a little bit of advice, a little bit of motherly advice, since we have Dr. Subbaranian here, okay, is don't take more than 16 hours a semester. Okay? In chemical engineering, that is a full load. All right? Don't work a job for too many hours a week. Okay? This is a job. College is a job for you. If you have conflicts between the amount that you have to work and the amount that you can go to school, okay, we would prefer you not to cut back on the number of your classes, but we're here to help you if that's what you need to do. Okay? So in general, if you're taking this full 16 hours, we suggest that you don't work more than 4 hours a week. If you're taking 14 hours, don't work more than 12 hours a week. And if you're taking 12 credits, don't work more than 20 hours a week. Okay? We want you to do well in school. We recognize that you have to have a work-life balance, and so these are some general guidelines that we've come up with over the years. All right? We are happy that you're a chemical engineering student at UAH. If you have any questions, you are welcome to forward them to us, and we will try to be there for you if at all possible. Thank you, and have a good rest of the day.